Yeah, thanks for the invitation to join you and present. It's great. I'm going to talk about a couple of different bits of work, but for the bulk of it, the modelling stuff at least, just need to acknowledge Alfie and Chris, colleagues in Liverpool who I've been working with. So what I'm going to talk about is basically this, two things: sediment routing systems, specifically the issue of how wide are shelves, how wide have they been in the past, and a few examples of numerical experiments, so using stratigraphic forward models in an experimental way. And I'll kind of show by example what I mean by that. Neither of these things are actually new. So, I mean, we knew about sediment routing systems and how important they were back in the mid-1990s onwards, right? But I think in the context of the future of deepwater sedimentology, both of these things are still important, and there's still mileage, kilometerage to get out of both of them. Okay, so hopefully I can demonstrate why I think that's the case. So talking about sediment routing systems first. So a key issue in this in sediment routing into deep water is how wide are the continental shelves, because they present a buffer to the transfer of sediment from river mouths into deep water, right? You probably all know this very well. And most shelves now on the planet are pretty wide. I mean, you know, up to a couple of 100 kilometers wide, where you've got river systems feeding into them, and in some cases wider for tectonic reasons. I mean, it's quite complex. But basically, that's a lot of that wide width is a consequence of very rapid Holocene eustatic sea level rise, glacial-eustatic. Now, we know from paleoclimate records, reconstructions, with which there's a fair bit of uncertainty, but we've still got a pretty good idea that kind of icehouse setting that we've had for the last 2 million years or so is relatively rare. It's not happened that much through Phanerozoic time. So this kind of raises the question, and what did greenhouse shelves look like? So in other words, what did these shelf settings look like when the climate was much warmer, when sea level wasn't going up and down at the same kind of rate? So here's our kind of hypothesized difference. The top diagram here shows wide shelves. Gray is the marine strata, and greeny yellow is terrestrial to shoreline strata. So you can see these sort of wide stretches of marine shelf that extend over a large part of the top of the delta cliniforms that form the continental margin. And what we're arguing is that the greenhouse morphology may well have been much more like this. Okay, but of course this is so much narrower. You can see these stretches of marine shelf are basically much narrower than in the icehouse setting. But this is just a hypothesis, right? So how do we test whether this may have been the case? So working with Ron Steele and Jinyu Zhang from BEG and University of Texas Austin, we've essentially measured examples of these systems, okay? And without going into lots of detail, we've got, I think, about 10 different systems and you know, several cliniform measurements from each. This spans a range of basin types, a range of different scales, different cliniform geometries, and most importantly, three different climate settings, essentially greenhouse, icehouse, and transitional. And you can see they're listed here in the set. And our method is essentially based on either well log, outcrop, or seismic data to try and reconstruct how far those marine stretches of rock extend into the top sets of the cliniforms. That's essentially what we're measuring. Now, when we do
excuse me, sorry that I have to interrupt you, but it's the setting that you have right now is in notes setting, so could you change into the full screen setting?
Yeah, I can do that. Yeah, it's just, I think it's just because they're on.
Just go, yes, go right on the display. Yes.
That better?
Perfect.
Okay, cool. Sorry about that.
Sorry.
That's just in the nick of time, because this is a busy diagram, so it's good to have it bigger. So this is the result of the study essentially, and what the takeaway points from here are that we've got 70 million years of geological time plotted on the x-axis, and then we've got the sort of the width of the total top set of these cliniform systems on the vertical axis, but normalized, so it goes 0 to 1. And what we're showing here is data from greenhouse systems, transitional systems, and icehouse systems. So green is greenhouse, yellow is transitional, blue is icehouse. And the takeaway point is that the mean widths for the greenhouse systems are substantially less than for the icehouse system. So this is what these data are telling us, right? So mean icehouse marine shelf width is significantly higher as a proportion of the total topset width than the greenhouse equivalents. So think back to that cartoon, it is pretty much like we drew it there. That does seem to be the case, at least for this data set. So we need to expand the study and probably look at more examples, and there are a few issues that probably need to be further explored. But I think what this poses as a question, you know, thinking of the future and future research, is then what then are the consequences of this for greenhouse Cretaceous, for example, age submarine fans versus, you know, Pliocene, Pleistocene submarine fans? The latter are not necessarily a good analog for those older systems because the narrow shelf is potentially going to make a big difference. So there's quite a few questions that are raised by this that I think are going to be exciting to pursue. Okay, so that's that. Now, numerical experiments then. This we've done, we've been doing these experiments using a couple of different models that we've developed over the past couple of years. So this is Lowbite 2D and Lowbite 3D, one being two-dimensional, the other being three-dimensional. They're both reduced complexity models. So Isabella Maciero, a former PhD student in Liverpool, myself and Alfie have been writing these codes, all deterministic, very simple, reduced complexity. They model sediment transport in a very simple way, but the really nice thing about them is you can model lots and lots of flows. So because they're simple, they run fast, okay? But they also do bed by bed detail. So this is important. So on this diagram, for example, each of those little red, orange, yellow layers, that's equivalent to one sedimentary bed. And a lot of stratigraphic forward models don't really resolve things at bed scale. They're more sort of general, you know, diffusion based, for example. They tend to be thicker intervals of not really bed scale strata. So this is quite useful to have a model that runs in this way. And I won't dwell on all of the maths and so on, but I just put this up to show you that it's reduced complexity, but physically reasonable. The essence of it is that flows move down the steepest descent route down a slope, and then when they hit a gradient threshold, they change from potentially from eroding or bypassing to a form of dispersive flow. Okay, and the erosion is modeled using some pretty classical equations, which give us some interesting behavior, but are very simple, you know. And the deposition is basically just spreading out of the sediment to form a lobe. So what kind of things do we get? Here's the gist of it then. The 2D model, what I want to show you here is just two examples, right, which illustrate what I think could be a potentially significant point going forward. So there's a top model here, and you can see that here's all the layers of the beds that are produced by the Lowbite 2D run. It's about 200 flows, okay? And this is the lower one. The second model is the lower diagram here, which is also 200 flows, but has got slightly different parameters, so a slightly higher erosion rate and a different grain size, okay? And the difference between those two architectures, you can see this is much simpler. It's basically very straightforward mounds. You can probably just about see lots of backstepping of deposits accreting on the back of a slope here as the flows come down and hit the topography and deposit, and effectively that drives backstepping. This blue-red diagram is a chronostrat version of that cross-section. So you've got distance versus the number of flows, so effectively time. Blue is deposition, so you can see that mound corresponds to this big blue blob, and that backstepping there corresponds to this blue wedge, which is diachronously backing up the slope, right? The point about this, though, is it's pretty simple. Solid areas of blue, solid areas of red, solid areas of bypass in between, right, where relevant. Okay, now, compare that, though, with this. This is much more complicated, okay? Simply by changing one or two parameters, we've switched from something that's quite simple to something that's much more interaction between the flow and the topography. It's much more complicated. There's multiple zones of bypass, erosion. There's a lot going on in there. We can characterize that with this SE thing, spatial entropy. Alfie just very excitedly sent me an email earlier saying that he got the code working so we can calculate the values. Basically, the spatial entropy is higher for the more complex version, and that's all you really need to know. Okay, so What this is showing us is complex strata from a very simple model. That's why I find it particularly interesting. The model couldn't really be any simpler. I mean, well, it kind of could, but it couldn't do anything interesting and be any simpler. It's pretty much as simple as it can be. And yet this contrast and that complexity I find actually fascinating. And I'm really looking forward with Alfie to actually exploring this further. He will be talking about this at BSRG in December, which is a UK Sedimentology conference. I think it's going to be at least partly online. So if you're interested, you can see more about this then. Now, just to finish off then, the 3D version, this is Lowbite 3D, and we're doing similar kind of numerical experiments with this, but sort of related but slightly different focus. And here I'm just trying to understand the nature of lobes in this kind of very simple fan strata, right? So you can see this is a picture of a Lowbite 3D run. You can see lots of the individually colored flows there are the different shades of red and orange. You can see this is the channel system that comes down the slope into the fan and then into the fan. And then each of those little blue dots is a apex point for one of the flows. And you can see they backstep up, they backstep up channels basically, and then fill the fan as they go. This is an example of the stratigraphy produced. You can see nice trends of thinning upwards beds. But the key point here is that there are lobes, what really do look like lobes developed in this cross section. So just expand on that a second. Let me just see if I can play this. Can you see that animating? So this is a run through of the model, a lot of those strike sections. So we're moving down the fan from its proximal apex towards its distal end. And you can see, if you look, there's a series of lobes here developed, separated by these muddy units. The grey is mud, by the way. The red and orange, again, are the individual flows. This is the chronostrat version of that. So you can see nicely separated in time, discrete groupings of the sediment that are effectively like lobes. Oh, sorry, I didn't mean to play that again. Let me just move on. Okay, so it looks like there are lobes in the model, but what I'm interested to try and do, what we're interested to do with Chris and Alfie then, is can we actually convert that sort of, they look kind of lobey, into something that's a little bit more quantitative? So this is my first attempt, and this is still very, very much in progress, to try and actually define how we would identify a lobe in this model output. So we've got a little flow chart that essentially calculates, when the model run is done, where the lobes are based on the position of one flow after the other, okay? And I won't go into the details of how it does it, but it's basically the position of each flow and whether or not the flow is separated from flows underneath by some sort of mud-prone hiatus. So, I mean, it's kind of what you would expect as perhaps a reasonable definition. And when we do that, we get something like this. Right, so the colors here are showing the different bits of sediment that have been classified as lobes. But interestingly, it's not actually straightforward. Even with that algorithm, it doesn't work as well as I thought it would. There's more complexity in here than you would first think in terms of how the different flow accumulations, if you like, the different lobey type bodies are connected to each other. So it's quite difficult so far, at least, to quantify exactly what is a lobe, define it in numerical terms, and then have the computer identify it automatically. This plot, by the way, is lobe volume through time. So it's how these lobes have grown. And you can see what happens is they grow very steadily and then stop. And that happens to some of them. And there's three bigger ones that are dominant. That's the brown, the green, and the sort of orangey color one. But then this red one is a bit more intermittent. It sort of grows, stops, grows, stops. So what we're seeing here is that there's a bit more going on than perhaps I would have first have imagined, even in a simple model. So here's running the model forward through time in plan view so that you can see this is the first lobe growing. And I think hopefully any second we're going to have an evolution. There you go. So you start seeing other things happening. And what seems to happen is there's almost like a transition period whilst the model tries to find the system tries to find a new sort of stable setting, which it then fills from, and then it switches again. There's another bit of instability, and then the next lobe sort of stabilizes and goes. So this is quite interesting dynamic behavior that we're now trying to explore and understand the consequences of. Okay, oops, I've done it again. Let me just move on. And what we also see is that if we run the model for longer, so 1,000 flows, it just gets more complex. As the basin floor topography develops, as you might expect, the interactions between the flows and the topography also develop. And it you can see that there are lobe-like things in here, but again, to define them explicitly numerically is surprisingly tricky. Okay, and I'll just very quickly run through and show you some of the complexity of this one in 3D as we scroll through it. And if you watch carefully, you can see that it looks like some of the lobes merge into each other and get more and less distinct as you move through the system. Okay, so there's a lot going on here. And remember, it's a reduced complexity model. So this is complexity arising from pretty simple inputs and very simple physics. Okay, because I can't code complicated physics. Okay, so, and then the lobe classification in this case looks like this. I mean, there's a lot of colors in there. And when you look at the lobes through time, I mean, it's like some sort of very complicated nightmare subway diagram. You'd have no way of finding Piccadilly Square on this subway map. Okay, so the takeaway message is there's a lot of complexity in a simple model. Even in 2D, that's the case. When you take it into 3D, you start to get the sense. So this is making me wonder about our definitions of what lobes are, particularly this idea about a lobe hierarchy. I'm not really seeing anything in here that could be classified in any way as a hierarchy in the sense that it's drawn in the standard sort of cartoons that are published. Okay, so one final slide. Results, and this is something I've shown a few times before, because the other thing that we're doing with this model is to try and understand how signals are preserved in this fan. It's a long story, been working on it for a few years, and it's surprisingly complicated. It's complicated because doing the robust time series analysis required to actually say with confidence when a signal is present and when it isn't is much, much, much more complicated than I think most people really explain in the literature. It's very hard, particularly when you're trying to do it across a couple of thousand model runs consistently in a way that allows comparison. Okay, so we're kind of getting hints that it's actually the short duration signals that are preserved best, which is counter to quite a lot of what's published, but this needs quite a bit more work. But it is something I think that this kind of modeling will shed more light on as we go forward. So here's my summary. The future of deepwater sedimentology, at least the contribution that I can make to that with and Alfie and Rob and Ron and Jinyu and the rest of us, right? Narrow shelves, thinking about the sediment routing system remains at the center of what we do, I think, in terms of understanding where the sediments come from, how much is going to go into deep marine settings. It remains a critical question. And then numerical experiments, I think these are going to be increasingly useful as we go forward, whether they're really detailed physics-based models or whether they're reduced complexity, things like this. There's a lot you can do with them if you take an experimental approach, and that's something I would emphasize. Run experiments with these models. Don't just run models to match them to outcrops. I don't think there's much point doing that, but if you run experiments with them, you can do all sorts of interesting things. Okay, so that is the kind of the last point. If simple numerical models can create complex strata, what is this actually telling us? Presumably the real strata are even more complex, and maybe we're just not really seeing that complexity in a lot of our conceptual models as much as we should. Okay, so that's it. And finally, I just put this because this is my favorite cat picture off the internet, the missing cat that isn't. Okay, thank you.